fine. So then, yes. So then, let's start. Then let's not lose time. So today, I will talk about fluorescence spectroscopy in time domain, so time-resolved fluorescence. And I will add also a section about quenching and also about FRET, because both they imply also lifetime analysis. So that's why logically I was putting it in this order. So after the time resolved fluorescence, can be that maybe everything is too long. So maybe in case I will see where we will be at 12, and maybe FRET I will just move it to the lecture of tomorrow, in case we don't. Is okay?
Yes, absolutely fine. So if
Okay.
you have
Good.
extra, you can
I
do
select,
next, yeah,
yes,
next tutorials or next lecture. Yeah, that's
exactly,
perfect.
exactly.
Okay, perfect. So,
So,
Simran, just a minute. Hello, Simran.
Yes, sir.
yes. Okay. So, you see my, that's, it's maybe, it's not the beginning. You see my slide in full screen?
Yes, ma'am. It's visible.
Oh,
It's clearly visible.
okay. That's good. So let's go.
Just,
Um,
just a minute, Simran. Simran,
Yes,
just
ma'am.
introduce a little bit. Simran,
okay.
yeah.
Good afternoon, everyone. Hello, ma'am. And welcome again to our web course. I hope you all had an insightful and an inspiring lecture by Dr. Alisa and Dr. Agasti yesterday. Now, I would like to introduce you all again to our international speaker, Dr. Alisa Bombada, on the topic Principles of Fluorescence Spectroscopy Part 2, Time Resolve. Ma'am, please start the lecture.
Okay. So thank you again for the introduction. And so let's go, and let's start with again the Jablonski diagram that we have already commented yesterday. Here, what is just added are the time scale of the different processes that are involved. So I just briefly go through it. So as you will see, so then we have absorption. Actually, it's the only, so there is no the time scale of absorption, but is power minus 15 second. So then it's very fast, practically considered immediate. And then, yes, it can be to S2 or directly to S1. So then with the internal conversion, and then we have the vibrational relaxation in the picosecond time scale. So here as you see, are the rate constant that are indicated. So that's why it's power 10 or power 12, but it will be picosecond range. And so from the first vibrational level of the electronic excited state, S1, there will be several phenomena of this excitation. And in particular, the radiative one is fluorescence, which is which also provided the rate constant of fluorescence indicate the time that the probe stay in the excited state, so which is about a nanosecond. Okay, so that is how we can construct the lifetime. So practically, the lifetime is it tells us, so the time it corresponds to the time the fluorophore spend in the excited state. And this, of course, is inverse to all the rate constant of the process that are imply the disexcitation. So the going back practically to the ground state. So if the radiative rate constant, that is the orange one, so the Kf, is much lower than the sum of all the non-radiative process, so like internal conversion, intersystem crossing, and quenching, and so on, fluorescence is practically not observable, is negligible, because practically it means that no photon are emitted, so we don't see anything. And yes, okay, so that is what is. Okay, so now there is a formula that is used to calculate, let's say, to estimate the radiative lifetime, which is practically, is also called the true molecular lifetime, which is really the lifetime of the
Excuse me, ma'am. Excuse me, ma'am.
See? Okay.
Ma'am. Excuse me, ma'am.
Yes?
Ma'am, your slides are not moving. Ma'am, your slides are still. Maybe you have not changed, or it's not moving. If you are changing your slides.
Okay. Sorry. I will, because actually for me I'm moving, but so
it is showing the first slide only.
Yeah,
where
I understand.
The
I understand. Because I maybe start again. Okay, so I think that is yes. Are now you are now are moving, eh? Is it okay?
No, ma'am. It's still the first title. No, ma'am. Not yet.
Oh, that's very bad. So I
okay, ma'am. Now it's moving.
Okay, so then I start again. So now you see? Did they change the slides?
No.
No, ma'am.
Oh la la. I don't know what to say, because for me it's okay.
Now it is changing.
So,
I think it is showing slide number 4 now.
Yes, and so, but now, I mean, it's not the full screen, but in the worst case, we can continue like this.
Yes, ma'am.
If it's better, so I reduce the side part, and so then okay, it's not full screen, but I mean, it doesn't matter. Okay, we will not have the animation, but okay, that's also is less important. And so what I want to say, so yes, we were talking just about the fluorescence lifetime, that is practically okay. You have it here. So what we were saying in the fluorescence lifetime is the time the molecule spend in the excited state, as is the inverse of the sum of all the rate constant associated to each process that imply the disexcitation of the fluorophore, so that the coming back to the ground state practically. And so, and here we have two categories: the radiative process, which is only one, which is fluorescence. So Kf is the rate constant of fluorescence, and the KNR instead is the rate constant of all the non-radiative process that are just is practically the sum of several rate constant. associated to the different non-radiative process. Okay, so the radiation lifetime, which is the inverse of only the fluorescence ray constant, is practically constant for a given molecule. So is a characteristic of the molecule. What instead is changing according to the environment are the radiationless pathway, which imply that the KNR, so all the non-radiative ray constant, can be more or less important. And so that means that this denominator, it can increase if the non-radiative process are more important, and therefore the lifetime decrease, because if you are more pathway that brings your molecule out from the excited state, the molecule spend less time in the excited state. That is logical. And okay, we were seeing yesterday that the quantum yield can be, which represent practically the ratio of the photon emitted by fluorescence on the photon that were necessary for exciting, that were used for exciting the state, can be expressed also in function of the rate constant in this way. So practically, it tells us what is the effect, how the radiative pathway is effective in comparison to all pathway of this excitation. And so, yes, here is okay. So so practically the fluorescence quantum yield is proportional to the fluorescence lifetime, as we can see. So that is, I hide this part because I don't know, I think that there was a problem in the, so as you see, the quantum yield, the QI, is proportionally to the fluorescence lifetime. Okay, so so in principle, one would say, okay, so they provide the same information, but yeah, not really. As we saw and as we will see also in the next. So, however, the measurement of fluorescence lifetime is more robust than measurement of fluorescence intensity, from which the quantum yield is determined, because the fluorescence lifetime does not depend on the intensity of the excitation, and also it does not depend on the concentration of the fluorophore. And the fluorescence intensity is proportional instead to the number of excited molecule, which depends of the number of the exciting photon and of the concentration of the molecules, of course. So that is a little bit the difference of the information. So the fluorescence lifetime, as the title say, is an intensive parameter. It doesn't depend from the concentration. The intensity instead, yes. So now I have to move the slides in this way. Okay, so this is a typical decay. So which is a schematic way to say which time range we can access when we measure the fluorescence decay. So practically, what is so-called the public life of the fluorophore, so is the experimental time window. And so then we can, with the studying the fluorescence lifetime of a fluorophore, explore the range that between the 100 to 10 times the fluorescence lifetime, approximately. And the afterwards, death is called, so in the sense that the fluorescence is so low that, I mean, we will not have any kind of information. And before, as we will see when we will describe the acquisition of the data, in the short lifetime, in the short time, so there is a convolution practically with the response function of the instrument, as we will see, that hide the information. But let's go. I think that the next should be about okay. So now, just I would like to explain why we talk about the exponential decay in general. So practically, this is a scheme of simplified scheme of the fluorescence process, and so it's practically is like to study a kinetic process. So we have okay, our molecule which is excited and it's finding the excited state. And when it's in the excited state, as two-way, so competitive pathway to come back to the ground state. So one is the radiative and one is non-radiative. So that is in the image. And this is, let's say, the reaction scheme, as we can so they are unimolecular practically reaction, and this is the rate equation that we can write based on this reaction scheme. The solution is an exponential. And the fluorescence lifetime that we are interested in is the time constant of this exponential. And actually here, so everything was modeled as a reaction scheme. So we considered the concentration of the species. Like in a reaction, as I said, of course, we measure the fluorescence, but the fluorescence is proportional to the concentration. So then, practically, if we solve it for the concentration of the excited state, then the decreasing of the concentration of the excited state, let's say, is described by a decrease in the fluorescence of the initial fluorescence, of course. That's this. Okay, so yes, okay. So now how to measure fluorescence lifetime? So there are two methods. One is in the time domain, and the other one is the frequency domain. So I briefly just cite the frequency domain, which is actually how it's working. So the excitation light is harmonically modulated with the circular frequency omega, and so also the emission will be modulated. But there is actually the emission in blue is actually has another type of modulation and also is shifted in phase. And by detecting, so there's using this parameter, this m and the phi and the frequency. So then using this parameter, it's possible to estimate the fluorescence lifetime. But it is a method that is less and less used, and is also limited to fluorophore that has one maximum two fluorescence lifetime, which is often not enough. So we will not go further with this method. What we will use is the time domain. So here is maybe more intuitive, because actually the molecules are excited by a very short pulse, which is indicated in blue at let's say at time 0. And the decay of fluorescence is then measured, usually by a method that is called the time correlated single photon counting. So and we have directly the exponential decay. So yes. Okay, so that is a typical scheme of the apparatus that is used. So as you can recognize the schema of the fluorimeter, because in fact we are measuring a fluorescence, so it's the classical 90 degrees configuration. But here what we have is a pulse laser. Normally then we have the sample. Then we select the pulse laser, of course, with that provide the wavelength with which we can excite our fluorophore, and then the emission. Then we have a filter for choosing the wavelength. Let's say, okay, so that's a very simplified. And finally a detector, which is normally a photomultiplier or a camera, and so on. Okay, so you see also you see that there are polarizers that are indicated, and since we were talking yesterday about the anisotropy, so normally the excitation is vertically polarized, and the emission is detected at magic angle, which was this angle that was able to produce a signal proportionally to the total intensity, and rid of any affection from anisotropic process. Okay, so how is working? So then here we have in light blue are the pulse that are there is a certain frequency, they are regular frequency are given, and of course every pulse means excitation of the fluorophore, and then the fluorophore after a certain time it emits a photon, and so you will see red is practically the photon emitted. What is measured is the delay with which the photon is emitted, and then is plotted in such a curve. So that says the decay that we were just seeing it before. So the time is the delay. So this is a schematic view of the time correlated single photon counting method. And so as you will see, so you have the excitation sources. So that is how it's working. Normally the signal, the excitation is split in two beam. One goes to excite the sample, and the other it provides a start signal. So practically it's saying when the pulse arrived. And then when a photon is emitted and detected, this is the stop time. So practically, we have there is in the electronics of this of the TCS-PC is possible to determine the delay between excitation and emission. and then this delay will be represented in the form of a histogram. So that's why it's single photon counting, because it's like we are counting the photon and putting them in two channels split evenly across the time range. And the profile of this histogram is the decay that need to be analyzed. Okay, so then I will just jump to, because here this also I wanted to avoid. Okay, yes, I will, I was, yes. So what I want to say, okay, so then this is an example of experimental data that one is obtained. And so as you see, so the decay is what is represented here, and what I indicate here with the arrow, which I hope you see. This is actually we can say the pulse. So is the so-called the response function of the instrument, the profile of the excitation, which should be in principle just a pulse with a negligible amplitude, but in reality it is not. And so we call it response function because in fact is measured in the beginning. So then and how is measured? Simply by scattering the excitation, so without the sample. So at the place of the sample is put this scattering material that deviate the excitation being in the detector. And so it can be the profile of the excitation can be measured. And this is something that has to be done in the beginning of the experiment. And so then, as you see, since the amplitude of this response function is non-zero, so it has to be taken in account in the analysis, because will definitely affect the very beginning of the decay. And so and in particular, and so the short lifetime. So the first operation that need to be done is a deconvolution, and afterwards the signal that is deconvoluted, so is get free of the contribution of the response lifetime, can be analyzed by non-linear fit. And here is two examples. So there are some continued distribution where you see the peak is representing the lifetime, and the peak and the and the area below the peak is the amplitude, or with more commonly a sum of exponential. So as you know, so we say fluorophore lifetime is the time that is spent in the excited state. So one was expected that the fluorophore has one lifetime, but in reality, it may have more than one. 2, 3 are very common. Then, I mean, more we have to see if there is a reason really to consider the more than this, and why there can be different lifetime. I give an example of the tryptophan. These are all data that correspond to the tryptophan, which is here, the fluorescent amino acid. So that is present with different rotamer, and which has different emission properties, and so also different lifetime. Then, of course, it can be calculated the mean lifetime, and that is in fact the average time that the molecules spend in the excited state in that way. Okay, so here is also another example. So again about the tryptophan. That is a protein actually for for information, is called the NCP7, is a protein of the nucleocapsid protein of the HIV-1 virus. And so it has two tryptophan in this position, and for each tryptophan has 3 lifetime, as indicated here. So then one would maybe expect that when we measured the protein containing the two, that no one was mutated, so it's the native protein with the two. So maybe we say we have 6 lifetime, but no, actually we get still 3. And so then it will be interesting to try to separate the signal of the two lifetime, because definitely this lifetime are sort of, has to be seen as a linear combination of the lifetime of the fluorescence properties of the single lifetime. And so with such method, we can practically recognize the contribution of each tryptophan in the fluorescence of the wool protein. Of course, the lifetime of each tryptophan will be weighted by the quantum yield of each tryptophan, which may be not the same, is not the same, and of course the fraction of presence. Okay, why this can be useful? So then we will see just afterwards. So this is the lifetime studies of the interaction of this protein with the nucleic acid. And so here we have the lifetime without the DNA. Sorry, that is the French version of calling it. With no nucleic acid and with the nucleic acid. So what we can see, and so then here we have a protein that contain a section, a mutated protein, practically that is only, is this portion of the protein that contain only one tryptophan in this position. That this is the protein where the zinc finger are not present, and it contains only the 61, and that is the wool protein. So here we have practically the contribution of one tryptophan, the second one, and here they are together. So what we can see is that when we have the nucleic acid, you see in blue, so you see that we have an additional lifetime, so 4 lifetime in presence of the nucleic acid. But you see that the 3 major lifetime, they practically respect the signature of the tryptophan 61.
So, hello everyone. So maybe some little bit connection problem. Alicia will come back again. Simran, are you hearing?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Hello. Your sound is mute. Yes.
Yes, here I am. Sorry, so you said the problem of connection, and actually
Connection.
I'm surprised. Yesterday I was at home and I was worried that the connection would have been unstable, and so today I say I come to the university, will be maybe better, but apparently not.
Mm.
So where now I just get the screen again, where it is now. I don't see it. Okay. Where do you see now the screen? My
Not slides. Screen
no
is,
slide.
yeah, not slides.
Also not now. No,
No,
no
no.
slides. A second. Present something else. Stop presenting. So, bon Dieu. Ignore. Okay. So how many things? Stop presenting. I will start the process again. I select the screen. But if I choose this, in principle, I should, I guess, allowed. And now you see the slides?
No, not yet. No slides.
Oh, no. I just close. I close other stuff, and I close this. Close that. So in principle, I don't know. I reopen I have also a very strange screen here. I see you with in 100 infinite copy, and I stop presenting and I try to do it again. So that's a presentation. Okay, the presentation is there. So now I will select the screen and somehow the presentation. So I allow. So now you see you see my screen practically now. Is it true? You see?
Yeah, screen is yes, but
Yes,
not
ma'am. Screen
not.
is visible, but not your slides. Screen is visible.
And now I make the slides. So now I open the slides, and do you see it? Do you see the slides? No?
No, ma'am, not yet. Like so many screens are coming.
Yeah, exactly. And so it's the same problem, and I don't know what to do. I don't know what to do because it's yeah. So I stop sharing again because somehow when before when I was select Windows or screen, before when I was making this operation, select window or screen, I was seeing it the slides in the list. Now there is not anymore. I see only the meeting screen, and when I selecting, then I multiplicate the
Ma'am, you can
windows.
do one thing. You can just left and rejoin.
Okay,
Maybe
I left the rejoin and we'll see. I will, I also, yeah, okay. So not now. So I left.
Your sound is in mute.
Yes, here I am, and now you see only me, no, because I didn't share yet. I will share. So I still not see the presentation, and it's amazing because if I do this, I'm afraid that. So now you see, yeah, you see. Do you see the presentation now? No?
No, you open
No.
your presentation. Now you open your presentation in your laptop.
I open the
Now you need to open your presentation in your
in
laptop.
my laptop, and it is
Yes.
open, and
Open.
it is open, but I'm sharing. Okay, I'm sharing Firefox, but it's why I don't see the in the list of sharing option. I don't see my presentation. That's why I'm sharing Firefox, because it's the only option that I see.
That's okay.
That's
When you
but
when
not
you're
really, because
sharing, you will not see your presentations, but you need to
yeah,
open the presentations.
and I open it. I now it's open. I see the presentation in front of me, but it's not share this screen.
Then,
And
did you select entire screen?
what I have to select?
Entire screen. You,
Entire screen.
yeah.
Okay, so let's see. Maybe. I stop presenting. Let's choose again. Um, Entire screen.
Yes.
Okay. So that was okay. So now, do you
Yes.
see it?
Perfect.
Okay. Bon, I don't know where the problem started. So this, you were seeing this, or I don't know.
No,
Is
we are in
you
slide
remember
number
the number?
15, I think. 14 or 15.
14 or 15. So that means practically here.
Yes, 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 yes.
Okay, then I start from here. So I just try to be to summarize a little bit. I even try to, maybe I try to go in full screen. Is it working full screen?
Yes, perfect, perfect.
Okay, that's good. So that's what I wanted to so that is practically an experimental result, experimental data. And the decay is, of course, the line is not complete, not really exponential, because it's a multi-exponential decay, yes. But you see also another line, which is the response function of the instrument. So practically the profile of the excitation, which should be measured before every experiment, and is done by putting a scattering material in the place of the sample, practically to deviate the excitation into the detector. And so when analyzing the experimental data, the first operation that needs to be done is to deconvolute to isolate the real fluorescence decay from the instrumental response function. Which should be actually a peak, very, in principle, should be a line, should be like a delta, a Dirac delta, but it's not. It's in reality has a certain amplitude, and which will go affect the beginning of the decay, and also and therefore the short lifetime. So the first is the convolution operation, and then with a non-linear fit to let's show, voila, which to extract the fluorescence lifetime with as a continuum distribution, like is represented here, where the area under the peak represented the amplitude of and so the weight of the lifetime, and or a discrete sum, a sum of discrete exponential. So as you see, so that's this data correspond to the fluorescence decay of tryptophan, which is just one fluorophore, and one would expect one lifetime, but instead it has actually three. And the reason why one molecule may have more than one lifetime is because it can be present in a different conformation. That's the case of tryptophan, which has different rotamers, and each one has a different fluorescence properties. What is instead unique is the mean lifetime, which represents the average time a molecule spends in the excited state. Okay. So yes, so that's just to give an example. So this is a protein which contains two tryptophan, position 37 and 61. For information is the nucleocapsid protein of the virus HIV-1. Which I was personally working, and each of these tryptophan has 3 lifetime. So when we detect the fluorescence decay of the protein, complete protein, including both tryptophan, are they 6 the lifetime? Actually not, are only 3. So that means that in here, the information associated to the both tryptophan is included, and it will be necessary to find a way to separate, and that's with this linear combination where practically that is the lifetime of the wild type that contain both tryptophan, which is seen as a weighted sum of the lifetime of each singular tryptophan, light blue 37 and dark blue 61, which participate with their fraction, so the contribution of the to the fluorescence of each tryptophan, which also has a different quantum yield. So, good. After this, we can then really analyze the protein because, for example, here is this protein in interaction with the nucleic acid. So that's are the lifetime that are detected without DNA, and that is with DNA. So these are the lifetime of the tryptophan 37, which was measured in such a portion where it was cutted, the part containing the 61. That is a version of the protein that contain only the 61, and that is the wild type that contain both. So here, just to guide you through the numbers, so just compare this the blue number. So you see that in the lifetime of the protein with DNA, so in the interaction with the DNA, we have 4 lifetime instead of then 3 without. Okay, one is very short, and the one that are not short are actually quite similar to the lifetime of the tryptophan 61. So that means that the interaction of the DNA affect mainly the tryptophan 37, and which is practically completely quenched. And in fact, it's indicating that could be, and the NMR was confirming it, in a stacking interaction with the guanine of the nucleic acid. And so practically silent, so then quenched completely. Instead, the tryptophan 61 is only marginally affected by the nucleic acid interaction, so the tail is there. So this is, for example, a type of information that can be obtained by the analysis of the fluorescence lifetime, also of a multitryptophan protein. Okay, so let's move on, since we unfortunately lost some time. So yeah, that's also quite interesting. So that's also the global fit of fluorescence decay, which is actually quite powerful way of analyzing the decay. So practically, the fluorescence decay are detected. So for a given the excitation is only one, and the lambda of excitation, but the decay are detecting a different emission wavelength. That's as you see, the color indicate, and you have different decay. And then in the global fit, all these curves are analyzed together, which of course has also some statistical advantage. And the constraint is say that the fluorescence lifetime that come out will be constant through the different decay. Instead are the amplitude that will be let floating dependent on as a function of the lambda of emission. So this kind of analysis that actually we are currently using in the lab improve the resolution of closely spaced lifetime, so because the statistic is better. Wavelength dependent contribution, we have we can analyze also the wavelength dependent contribution of the components over the emission spectra, and we can also calculate the time resolved associated spectra and the decay associated spectra, which we will see here. So practically, time resolved associated spectra, as you see, are so this is the different decay that are recorded at the different wavelength, and then imagine to through along this dimension, which you make section of the yes, of all your decay. So practically, and if you follow the profile of the section, you will get a spectrum, because here along the green axis you have the lifetime. And so then, is for example, the black arrows here correspond to the short lifetime. So that is practically, this is the profile of that we can have at short lifetime. And if you take the at longer lifetime, the light blue, so then that is the profile that we can have a longer lifetime. So we have slice of intensity wavelength plane. So practically how the spectra evolved with time. Yes. Okay, so with this method, so with the time-resolved emission spectra, they are used to characterize, for example, the solvent relaxation that we have seen yesterday. And so this is practically in a schematic Jablonski diagram. So the solvent relaxation imply that the emission is shifted at longer wavelength because the relaxation decreases the energy of the excited state, the relaxation of the solvent around our fluorophore. So fluorescence is excited by short pulses. Photon emitted shortly after the excitation pulse come from molecules in non-relaxing state. So then the dipole of the floor of the solvent didn't succeed to orient according to the emission dipole of the molecule, not yet. So there has not enough time to relax. At longer time after excitation pulse, instead, the state is more relaxed. And so, and these are the spectra, the color, following the color code, that are the spectra that can be obtained by the method that I was showing you afterwards. And then if we practically follow the shift of the fluorescence maximum in time, because that's the spectra obtained after 0.1 nanosecond, and the red one is after 10 seconds. So we practically can have a sort of the kinetic of the relaxation process. And the time scale of solvent relaxation is largely determined by the mobility of the solvent around the fluorophore, and so of the local viscosity. So this type of experiment open an eye practically on such phenomena. So good. And then we can also calculate the decay associated spectra that, so the global analysis, as I was already explained, so that is where we have that is the function of the global analysis, where the amplitude depends on the wavelength, but the lifetime, no. And so then, using the data that we obtain, so we can calculate, so using the amplitude, combination of the amplitude and the lifetime, we can calculate the decay associated spectra. So practically are spectra that are associated to the species characterized by a specific lifetime. And so here is that's why decay associated spectra. So there are the spectra associated to a lifetime. And so with such type of analysis, it was possible to characterize the spectra of the two tautomer of this molecule, which has a different lifetime. So you see that it's practically the dotted line are the decay associated spectra, so that are calculated for the longer lifetime and the 16 nanosecond lifetime and the 6.8 nanosecond lifetime, which very well overlap to the fluorescence spectra of the so-called H1 tautomer here in red and the H3 tautomer in blue of this molecule, indicating then that the lifetime, so that's the 16 nanosecond is the lifetime of the red species, and the 6.8 nanosecond is the lifetime of these species. Okay, that's it. Sorry. Okay. Okay, so then practically we attributed the lifetime of two different tautomers of this molecule. And okay, so voila, that's we'll see what time is it. Yes, okay, we have still 1/2 hour. Okay, that was in general about lifetime. Now we'll see a chapter about quenching, which is where lifetime also are involved. So that is quenching by external quencher. So that means that the experiment in this case are practically done by adding molecules that are known to quench the fluorescence and to measure the fluorescence intensity or decay in function of the concentration of such quencher and getting information out of it. So here I remind the quantum yield, the definition of quantum yield and of fluorescence lifetime. In orange is the radiative rate constant, and in black is the sum of the non-radiative rate constant. One of them, it will be the quenching rate constant. We can divide the quenching process in two major categories. The collisional quenching, also called the dynamic quenching, and the static quenching. So in collisional quenching, so we have the fluorescence is quenched by collision with the quenching molecule. So that is practically, again, a Jablonski diagram, a very, very schematic. So we have the excitation, then the vibration. So then here, that is the fluorescence level, let's say. And this is the non-radiative pathway due to the quenching. And of course, it depends since quenching is a molecule, so then which will interact with my fluorophore, it depends on the concentration of the quencher. And that's when we plot the ratio between the initial fluorescence and the fluorescence in function of the 4 different quencher concentration, we have normally a straight line that indicate that F, of course, decrease with respect to F0. And a straight line is also obtained by, if we plot also the lifetime without quencher divided by the lifetime in presence of quencher. In the case of static quenching, the mechanism is a little bit different because the quencher practically interact with in the ground state with the fluorophore, and it this produces species that is non-fluorescent. So we can get the fluorescence only from the fluorophore that did not interact with the quencher. But if it was interacting, the molecule is the complex, let's say, is not fluorescence. So in this case, the fluorescence will decrease because the concentration of fluorophore able to emit decrease, but the lifetime is not affected, as the straight line indicate, because the fluorophore that emit has always the same lifetime. It continue to emit the portion that is free from the quencher. And since the lifetime, as we were saying, is an intensive parameter, it doesn't depend on the fact that the emitting fluorophore are less, it's not affected. So that is a signature of the static quench. Also, a way of to try to distinguish between the two. Sometimes, if you you cannot make a lifetime experiment, is also to use the temperature. Normally, the temperature favorizes dynamic quenching because the probability of collision increases. Instead, this favors static quenching because the complex are more loose. So that's okay. Okay, collisional quenching. These are common quencher that are used. So O2, iodide, cesium plus, and also acrylamide, and this is the Stern-Volmer called equation that describe how the fluorescence decrease with respect to the initial one is 0 in function of the quencher concentration. And in the constant, in the Stern-Volmer, S and V stay for Stern-Volmer constant, we have the information on the rate constant, the quenching rate constant, KQ. Okay, well, that is one example. So, of course, from this straight line, so the coefficient of the line will provide the KSV, and then knowing tau 0, which is the lifetime of the molecule without quencher, then we can calculate the quenching rate constant. Okay, so just I think yes, and when it's purely dynamic, of course, the same equation and the same profile, we will have it for the intensity and the lifetime. Okay, the Stern-Volmer equation comes from this scheme. So again, Jablonski diagram that we saw already. That is the quenching pathway due to the collisional with the quenching molecule. That is the decay, representing the decay of the fluorescence. And this is the fluorescence lifetime without quencher, and this with an additional pathway due to the quencher. So that is, and so if we combine this lifetime, so we in this equation, comparing practically tau 0 to tau, we arrive to the Stern-Volmer equation. Moreover, since quantum yield is proportional to the fluorescence lifetime, we can understand why the intensity and the lifetime have the same evolution in case of this type of quencher. So the decrease in lifetime occurs because there is an initial rate process that depopulates the excited state, this one, and the decrease in quantum yield occurs because quenching depopulates the excited state non-radiatively. So less photon finally. Okay, that's is actually the model of some two mechanisms of fluorescence of static quenching, and the most intuitive is the one that occur because there is a formation of a non-fluorescence complex, as we were saying. So it's practically there is this reaction that is occurring and the complex is non-fluorescent. And so if Ks is practically the stability constant of the complex with the quencher and the molecule, we can obtain the equation that link the intensity without quencher and the intensity in presence of quencher. So practically, this is a curve that is normally, as you see, is hyperbolic type. And instead, the lifetime, as we said, didn't change. Okay, there is also a little bit more complex model with the sphere of effective quencher when practically the quencher is not really forming a complex, but it's quench when it is in a sphere, when it's close enough. And so this is, let's not enter into details, just I say that exists. So that is normally, it based on the probability of the presence of the quencher in the sphere of effective quencher. And so then the is, how to say, an exponential behavior. So not exactly hyperbolic, but difficult to distinguish when you have just a few points. So then a similar curve. Okay, so that's the molecular model. And of course, sometimes both occurs. And so then this is a way of combining both. And so when there is collisional, the contribution of collisional quenching and the contribution of static quenching. And so then it's required, so fitting the data practically, we may have information on the constant, on the parameter characterizing both. And that will be the type of curve that one would obtain. Of course, in this case, also the lifetime will change because of the contribution of the static quenching. So, yes, okay, I maybe just cite this, and I see, okay, oh, we still have 10 minutes. Okay. So, yes, so then we saw the two major model of a type of quenching, and then we can also have non-linear Stern-Volmer plot in case of purely collisional quenching, that we were expecting normally to have a straight line, but and so this may happen when, for example, we have a protein that has 2 tryptophan, more than one, let's say 2, can be already enough. And the one, these are the 2 fluorophore that will be analyzed. And the one is accessible to the solvent and the other to the solvent, and so to the quencher, and the other not. And so in this case, so there is only collisional quencher. When quenching there is collisional, maybe, but the curve is a bit different. Is not linear as expected because of the contribution of the fluorescence of the tryptophan that is not affected by the quencher practically, or less affected in a different way. And so that is an example of work. So this is a protein, liver alkyl dehydrogenase that has 2 tryptophan. One is buried and one is on the surface, and that's where the quenching curve with iodide, which is really a quencher known for for the mechanism of quenching of iodide is dynamics, is collisional. Moreover, is charged, so then it's practically affect mainly the surface, what is exposed then to the solvent. It doesn't enter into the core of the protein. And so, yeah, then here that's where this curve were obtained, were measured at the different wavelength. The 350, which means in a polar environment. Let's consider the story of the solvent relaxation, and so it's mainly attributed to the tryptophan that is exposed, and 323 instead is attributed to the buried tryptophan. So the contribution is higher. So practically, that it shows that the different emission wavelength, so this different emission wavelength report on the two different tryptophan, which are, of course, whose fluorescence is quenching at a different extent by the quencher that was chosen. Okay, the very last argument on quenching, so is also is a way of analyzing this unusual Estelle-Bolmer plot. And so here is again considered the effect of one protein that contain 2 tryptophan, so on to 2 tryptophan, 2 fluorophore, let's say, one that is which has a different fluorescence signal. So then and the fluorophore A is not accessible, and B is non-accessible to the quencher, let's say. So the total fluorescence in absence of quencher is, of course, can be defined like this, with the contribution of the fluorescence of the 2 fluorophore. And in presence of quencher, instead, will be can be represented, characterized like this, where the one which is not accessible to the quencher is practically not affected, and instead is affected only the one of the fluorophore on the surface. Okay, so then some mathematical manipulation. So that is the difference between these two equations. And then we make the relation between F0 and F0 minus F. So rearranging, we get to this kind of equation, which, and if we plot this quantity F0 on F0 minus F in function of on the reciprocal of the quencher concentration, we will get a straight line, and the intercept will give us the fraction of the initial fluorescence, determining that like this, that is accessible, let's say affected by the quencher. So that is with this model, we can get this information. So here an example in which this model was used. So that is the protein L03, which contains 2 tryptophan, 1 exposed and 1 buried. These are the experimental data. That is the unusual Stern and Wolper plot that was obtained. And that is the linearization done with the model. And the intercept is 2, indicating that the fraction is practically almost 0.5, the fraction FR. And so the conclusion of this study is that 1/2 of the emission can be quenched by the iodide. And so that means that the conclusion of the study, so that's is that both tryptophan residues in L03 are equally fluorescent, but only one can be quenched by iodide. So that is the conclusion of the study. Of course, the publication is, there are many other evidence and so on, but somehow this data, this analysis is coherent with such conclusion, and this is an example of the information that with the quenching studies with quenching experiment can be obtained. So yes, yeah, okay. So just since that was a work of mine of some time ago, I just show also this experiment. So that is practically we do the tutorial together with the lecture. So that's is one zinc finger, actually again of the nucleocapsid protein of HRE1. And this is it was a quenching study was done for the wild type and different mutant, 4 mutant, where each residues coordinating zinc was mutated in a non-coordinating one. And so quenching experiments were done, and these are the quenching rate constant that could be extracted by this experiment. And what we see that the highest, so the practically quenching is more effective in the wild type than in the mutant, and in particularly the mutant that make flexible the chain containing the tryptophan, which is our reporter. and even lower in the apopeptide that do not contain zinc. So this study, which initially was for us a bit surprising, because normally when you unfold the protein, you normally expose the tryptophan to the solvent and so on. But actually here the conformation was different. And that means that the tryptophan in the wild type is really well exposed, quite external, and to the solvent. And instead, in the apopeptide, so let's go immediately to the extreme case, where the chain is completely flexible. Then the tryptophan will get involved to will practically have additional will be practically somehow protected a sort of statistically in percentage, of course, by the chain that somehow cover around the tryptophan. So there are some structures that are a little bit the change that are dynamic, but somehow statistically maybe interfere with the quencher, with the quenching process. And in the mutant, which has an intermediate flexibility, we will have all the intermediate case. The mutant that is closer to the apopeptide, of course, is the one that is making flexible the chain around the tryptophan. Okay, so I think that I will maybe stop here, and for I hope that you agree. I don't want to to exaggerate.
Yes, it is perfect. Yeah.
Is okay.
Yes.
So
So,
okay, so that.
yeah. Do you have any questions from the students? So, any queries, questions?
Something that was not clear, was surprising you, and then you want to get more insight. Okay.
Can you conclude?
So okay, so then we conclude, and so then I will say that since I consider that FRET is quite an important topic, I would like to then tomorrow in the lecture we will talk about FRET, and then we see how we will evolve, and in case we can start also the lecture that actually was planned for tomorrow. So or maybe I reorganize a little bit the argument, because I see that there are many things to say, and but maybe not everything can be said.
Yes. So,
Okay.
yeah.
Yeah. Let's do like
That's
this.
perfect. Yeah.
Okay.
Okay.
So,
It is a very excellent and nice talks, Dr. Elisha, and
okay.
all the participants. You can hear every day. Elisha have lectures, and she will explain more details of these biomolecules with this fluorescence technique and fluorescence probe in protein, DNA, and its applications. Okay, so we'll see in the next lecture also. Alicia tomorrow have
yes.
same times. So
Yes.
okay,
Yeah.
thank you so much, Alicia. For
Okay. So
excellent.
then, so have a nice evening, I guess,
Yes,
and see you tomorrow. Okay,
same.
the same time. Good. Bye bye.
Thank you so much, everyone, for watching this lecture. Now, I would like to introduce you all to our next speaker, Dr. Pamita Avasthi. She'll has this tutorial lecture today. So I would like to welcome ma'am for her lecture.
Okay.